Hi, this is Professor Fernandez, and in this video, we're going to work on an example of L'Hopital's rule. So this example comes from the lesson notes for Lecture 9 in the Calculus 2 course I'm teaching. You can find those notes on this site and in addition, all these other resources. So the first thing I'll say about this video is that I really want to encourage you to check out the video that preceded it, video 9.1. In that video, I talk a lot about L'Hopital's rule. I'll just zoom in to the lower right-hand side here. I go over this theorem where I talk about indeterminate forms, what they are, why they're called indeterminate, and specifically about these two, 0 over 0 and infinity over infinity, the two that L'Hopital's rule is really designed for. And then what it means to apply L'Hopital's rule, right? Which is that if you take the limits as x goes to whatever, of a quotient, f of x over g of x, and you get one of these indeterminate forms, then L'Hopital's rule tells you, hey, it's equal to, the value of the limit is equal to the limit of the ratio of the derivatives of f and g, provided that the limits exist or tend to infinity or negative infinity. Okay, so again, I'll send you, that was a very brief overview because I really want to send you over here if you want more details. So let me now then pivot to talking about the example for this video. Let's zoom in here, evaluate this limit. Okay, and one of the things I'm going to do in this video is to show you how to extend L'Hopital's rule to be applicable to other types of indeterminate forms, not just 0 over 0 and infinity over infinity. So let's do the Calc 1 thing here, and let's try to just substitute in this x equals 0 from the right into wherever I see an x. So I would get sine of 0 from the right raised to the 0 from the right. What does this mean? So this means that this is sine of a tiny, tiny number that's very close to 0 but positive. So that's going to be basically 0. Raised to the tiny, tiny number but very close to 0 and positive. So that's also basically 0. So this is not a type of legitimate, I would say, answer to a limit. This is like 0 over 0 and infinity over infinity in that it is an indeterminate form. Again, in video 9.1, I talked about what that means. Long story short, in this context, right, you can come up with different functions like x over x, 2x over x, 3x over x, whose limit as, for example, x approaches 0 of all these functions appears to be, using the just plug in the thing, 0 over 0 in all cases. But in fact, the answer to this limit is 1. The answer to this one is 2. The answer to this one is 3. So that's one reason why 0 over 0 is an indeterminate form. You can't determine the value of the limit just by knowing that it tends to 0 over 0, because the value might be radically different based on the particular limit you're looking at. Same thing happens for infinity over infinity, and the same thing happens for 0 to the 0. In fact, here are other indeterminate forms that if you see in the wild, you should not stop and say, all right, this is the answer, because the answer might be different, right? It might be the same thing that's happening with these two other indeterminate forms. So for all of these, if you get a limit that tends to one of these quantities, then you know that there's got to be something else going on. There's got to be a different way to evaluate the limit, because these are not going to be actual unique answers for a limit as they should be. Okay, so what am I going to do instead, right? Knowing that I now have one of these indeterminate forms. Well, that's the point of this video, to show you how to deal with these particular types of indeterminate forms, specifically the ones that are powers, right? Here we got 0 to the 0, but everything I'm going to talk about works just as well for infinity to the 0 and also 1 to the infinity. Any one of these power indeterminate forms, something raised to the something. So what am I going to do? I'm going to say, if you were to graph this function to get some sense of what the limit is, you'd probably, you'd write down y equals sine x to the x, you'd graph it. How about we now take the natural log of both sides? You might be wondering, why would I do this? And I would say, give me 5 seconds. And the math will tell you exactly why this helps. If I do this, the right-hand side is ln of sine x to the x. And remembering one of our logarithm properties where we bring down the exponents, right? This right-hand side is x times ln of sine x. Okay, so at this point, let me talk about why this simplification helps. Suppose that I wanted to now take the limit as x goes to 0 from the right of the entire equation. On the left-hand side, I would have the limit as x goes to 0 from the right of ln of y. But remembering that ln is a continuous function, ln of x, this limit would slide right inside, and I would have limit of, ln of the limit as x goes to 0 from the right of y. Okay, remember, y is the function sine x to the x. It's exactly what we want to find the limit of. So in fact, the original limit that we wrote down up here, we could write as limit as x goes to 0 to the right, from the right of y. That's exactly what's in here. Okay. On the right-hand side, right, this would be limit as x goes to 0 from the right of this function. So x ln of sine x. Okay, let's say just for the sake of argument and illustrating, how this ln of y business really helps. Let's say for the sake of argument that this limit, this whole limit ends up being 10. Let's just say. So that ln of the limit as x goes to 0 from the right of y equals 10. Then we would say, oh, this is really nice, because if I just exponentiate both sides, then I get that the limit as x goes to 0 from the right of y equals e to the 10th. That is literally the answer to the limit that we're looking for. Aha! So you see now how this approach of starting with the function over here, starting with the function, taking the natural log, and then doing the simplification we are about to do in a minute helps. Because if we're able to do that, and if we are able to actually find a value for that limit, then at the very end, all we do is we exponentiate that limit, right? In other words, if the answer here was 10, we do e to the 10, and that's the value, the answer to our original limit. Okay, so I'm going to erase all the stuff that we just did, which was for the purposes of giving you an intuitive sense of where we're heading and why we're doing what we're doing. And now I'm going to actually dive into doing the thing, right? Figuring out what the value of this is as x goes to 0 from the right. Okay, so notice that if I try the Calc 1 thing, right, where does this head as x goes to 0 from the right? Well, the x here goes to 0, basically. And there's an x here. So this is ln of sine of 0. And sine of 0 is 0. So ln of 0. ln of 0 is minus infinity. So this thing heads to 0 times negative infinity. If you rewind this video a few minutes, you'll see that this is one of the indeterminate forms that I mentioned. One of the other indeterminate forms I mentioned, aside from 0 over 0, infinity over infinity, it was in this category that I wrote up earlier of these other types of indeterminate forms. It doesn't matter, by the way, that it's negative infinity. I talked about 0 times infinity. It doesn't matter that it's 0 times negative infinity. That's also indeterminate. So the question is, what do I do with that now? Well, like we talked about earlier, L'Hopital's rule is intended to work with indeterminate forms of this type. So it seems at first glance that it might not be able to handle this. But that's just a difference in how we view things. Because 0 over 0 and infinity over infinity are different ways to write this indeterminate form, and vice versa. So let me show you what I'm talking about by going back again to our example. So we now know that this goes to 0 times negative infinity. If we want to convert it to one of these other indeterminate forms, here is a fact that we could use, right? This function, I'm just going to write it down and then talk about it, is equal to this other function, where other is in quotes because they're the same function. Okay, so how do I know that? Well, so let's do the math here. So ln of sine x over x, ln of sine x divided by 1 over x, right? That's what's happening here, equals ln of sine x multiplied by the reciprocal. All right, so, and that's x ln of sine x. That's the original function we started with. Okay, so this shows us that these two functions are in fact the same function. So that's nice. And why would we do that? Well, because check out what happens now. As x goes to 0 from the right, the numerator still goes to negative infinity, right? Sine of 0 is 0, ln of 0 is negative infinity. So the numerator goes to minus infinity. The denominator, Well, as x goes to 0 from the right, 1 over 0 from the right is positive infinity. So the denominator goes to infinity. So we now have an honest-to-goodness indeterminate form that L'Hopital's rule can handle, right? So again, let me recap what happened, right? We started with the function. We tried to take the limit as x goes to 0 from the right. We obtained an indeterminate form, but not one of the two that L'Hopital's rule is built for. So we did some algebra, right? We took one of the functions and we expressed it as 1 over that function. And I phrase it that way because this could have been sine x, could have been tangent, whatever function. When you divide by 1 over, it's algebraically the same thing as multiplying by the function. That's all we did. And then when we reevaluated that limit, now we got something that is something we can handle with L'Hopital's rule. So that's nice because that's exactly what we're going to do now. Okay, so let's go ahead and do that. So L'Hopital's rule says that the limit as x goes to 0 from the right of this function is the same thing as the limit as x goes to 0 from the right of the ratio of the derivatives. I'm just going to write that first, and then we will calculate the derivatives next. Okay, so what are these derivatives? Well, in the denominator, I have 1 over x, that's x to the negative 1. That is going to be a power rule, so bring down the negative 1, subtract 1 from the exponent, so that's 1 over x squared with a negative. In the numerator, I'm going to have to do a chain rule, right? The derivative of ln is 1 over whatever it's the ln of, in this case sine x, and then times the derivative of that thing. That's the chain rule step. Derivative of sine is cosine, so this is cosine over sine, otherwise known as cotangent x. So that is the new numerator over here. All right, now I do my L'Hopital's rule thing. I try to reattempt evaluating the limit, right? What does this go to as x goes to 0 from the right? Let's try it out. Cotangent x, well, that's sine over cosine. So as x goes to 0 from the right, this would go to cosine of 0 over sine of 0. I'm ignoring the to the right, to the left, because it doesn't really matter for these purposes, given the specific functions we have. Okay, cosine of 0 is 1, sine of 0 is 0. So this is some form of infinity, right? The plus or minus here could determine the plus or minus here, but it doesn't matter because we're just looking for, are we heading toward infinity, and then that will tell us the limit doesn't exist. Are we heading toward a number that tells us what the limit value is, or are we heading toward some other indeterminate form? The denominator, as x goes to 0 from the right, again goes to like 1, minus 1 over 0 squared. So this is like negative infinity. So we get infinity over infinity. That's another indeterminate form. So like we talked about in the previous video in this playlist, video 9.1, sometimes you have to do L'Hopital's rule more than once. But what I'm going to layer on in this video, and that's the point of choosing these examples carefully, the ones that I choose, is that you want to think a little bit before you just blindly apply L'Hopital's rule one more time. Because you might get yourself into sort of an infinite loop of applying L'Hopital's rule. That could happen here. If you just go here, apply L'Hopital's rule, it'll get more complicated, and then it'll just keep going, never end. However, if you simplify the function first, and then apply L'Hopital's rule, then you're one step away, basically. How do I do that simplification? Well, I'm dividing by minus 1 over x squared, so I'm going to put that in the numerator. And cotangent x, remember that's 1 over tangent x. So I'm going to put tangent in the denominator. So this is a new function. Okay. Let's look at what happens here. As x goes to 0 from the right, the numerator goes to 0. The denominator tangent of 0 is 0. So I get a different type of indeterminate form, 0 over 0. Question, does it matter? Infinity over infinity or 0 over 0? Answer, not really. They're both indeterminate. However, as I said earlier, or hinted to at least, applying L'Hopital's rule on this, you're one step away from the answer. Applying L'Hopital's rule here will kind of throw you into a loop where you seems like you'll never get done, right? And also, by the way, derivatives of cotangent are a little more tricky for most of us than derivatives, for example, of sine, cosine, or tangent. Okay, so I'm going to apply L'Hopital's rule one more time here. Let's see what happens. So derivative of the numerator is minus 2x. Derivative of the denominator, derivative of tangent, is secant squared. Okay. Now I reattempt applying L'Hopital's rule. The numerator goes to 0. The denominator, secant of x is 1 over cosine of x. So secant squared is 1 over cosine squared. And as x goes to 0, this goes to 1 over cosine of 0, which is 1. So the denominator goes to 1. So, aha, I get a number. So this whole limit equals 0 over 1 equals 0. Great. So I don't have to apply L'Hopital's rule again. Now, question, is this the answer? No. Remember, if you rewind the video, we had talked about, I erased it, it was down here. The fact that, I'll write down what we have now. Since we've gotten the limit as x goes to 0 from the right of this equation, what we started off with, right? I'll rewrite some of it to remind you. We have now figured out what the limit of the right-hand side is. This limit is 0, right? That goes here. So we now have the limit as x goes to 0 from the right of ln of y equals 0. And remember I talked about, a few minutes ago how this limit slides in here because ln is continuous, and how then basically it's ln of the limit as x goes to 0 from the right of y equals 0. And then we can just exponentiate both sides, and then those go away and say, oh, the limit as x goes to 0 from the right of y equals whatever this happens to be. E to the 0 happens to be 1. So this limit that we were trying to find all along up here, right, equals 1. That is the answer to our limit. So I'll just write it over here. Okay, a few things I want you to take away from this video. Number one, right, there's a bunch more indeterminate forms than just these two. So rewind the video to the beginning where I wrote out some of the other ones that you run into in practice. Number two, for all the ones that are something to the something, right, infinity to the 0, 0 to the 0, 1 to the infinity, for all of these, the method that we applied here, taking the natural logarithm of both sides, is going to work, and it's going to work very well. However, at some point, you have to, here, for example, when we did this step from here to here, you have to put the limits into, the new limits you're getting, into one of these L'Hopital's rule forms. So that might involve, like, if this is an x, divide by 1 over x. Algebraically, it's the same as multiplying by x, gets you back here, but it actually helps you to get into that 0 over 0 or infinity over infinity form. And then two last things. When you are thrown into applying L'Hopital's rule and you have to do it more than once, think about algebraic simplification before you apply L'Hopital's rule, right? It could save you more applications of L'Hopital's rule, or kind of like an infinite loop of you just keep applying L'Hopital's rule and you can't get a final answer for the limit. And then last one, in this method, because you took the natural log of both sides, right? Whatever value you get for the limit is not the end answer. That is ln of y equals that answer. So to find the actual value of the limit, you exponentiate that answer, right? So that's why we did e to the 0, turns out to be 1, and then that's the value for the limit. Great, thanks for watching.